Hi everyone. So we'll talk about titrations here. Let's say you want to determine the molarity of a base solution or an acid solution or an oxidizing agent or a reducing agent. You can do all that with titrations. Let's say that you wanted to determine the molarity of a barium hydroxide solution before using it to determine the molarity of something else. Maybe you want to make a around 0.04 molar barium hydroxide solution. Well, you might think that you've made that, but it's probably not exactly that. Hydroxides absorb some water from the air, so we need to standardize this solution first. Make sure we know its exact molarity approximately. So we can know the molarity of this base solution by seeing how much of it is needed to react with this acid. You can add, maybe you need 22.0 milliliters of this barium hydroxide solution to neutralize these 0.34 grams of KHP. KHP is potassium hydrogen phthalate. It's actually not a potassium, a hydrogen, and a phosphorus. It's potassium hydrogen phthalate. This is just a symbol for that phthalate, that P. So we can use this because it doesn't absorb water from the air. When we use a certain number of grams of it, we actually know that it should be fairly pure. We know the number of grams of it, and therefore moles of it. And from that, we can find out how many moles of KHP were needed then to neutralize it. And so we can add that barium hydroxide, drip, 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 to the KHP solution. We should get a color change when we've added just enough of that base solution to drip, 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 react all of the acid there, KHP. That color change comes because we have an indicator present, phenolphthalein in this case, which would turn pink once that solution turned basic. It would turn pink once all of the acid is gone. That point is called the equivalence point, when you've reacted all of the thing that was at the bottom. This KHP, I am going to kind of just symbolize it with HA. This is a generic monoprotic acid. There's just one proton H on that conjugate base, the A minus. You can use this for plenty of other monoprotics as well. HA is the generic symbol. Now the thing about KHP is it has a molar mass of 204.22 grams per mole. I think you'll need this in one of the problems on the worksheet. So if we know how much KHP was there, how many grams of KHP were there, we will know how many moles of KHP were there. And we will therefore know how many moles of barium hydroxide were needed to neutralize it. We will be adding just enough moles of barium hydroxide to neutralize that KHP. That's going to be in a certain ratio, 1 to 2, which we'll get to in a moment. And then after knowing the number of moles of barium hydroxide, we can know the molarity of the barium hydroxide solution, seeing that we needed just 0.022 liters of it, or 22 milliliters of it, to neutralize. So why do we have a 1 to 2 or 2 to 1 ratio here? It's because we are dealing with barium hydroxide, which has 2 hydroxides on it. If you want to have a complete neutralization of this compound, you need to react both of those hydroxides. Every OH minus needs to combine with 1 H plus to form water. So if there are 2 OH minuses, you'll need 2 H pluses to neutralize them and form 2 waters. And so you'll need 2 monoprotic acids, 2 acids that each have 1 proton on them. So 2 monoprotic acids are needed to neutralize something that has 2 hydroxides. How many HAs, how many monoprotic acids would you need to neutralize 3 OH minuses? It would be 3, right? So you won't even need to write out this balanced chemical equation on the problems or a quiz or test. Just know that you need for every OH minus, you need one H plus. Okay, so kind of going through that map again, going through the math, we had 0.34 grams of KHP, which had a molar mass of 204.22 grams per mole. So we knew the number of moles of KHP, and then we knew for every 2 moles of KHP, there was 1 mole of barium hydroxide present. So we had dripped down into the solution at the bottom that many moles of barium hydroxide. But we added those moles of barium hydroxide in 22 milliliters or 0.022 liters. So therefore, this was the molarity of that barium hydroxide solution.